Hello, everyone. I'm Courtney Chambers, your webinar host from the Engineer Research and Development Center. I'm glad you could join me for today's webinar brought to you by the Ecosystem Management and Restoration Research Program. It's good to be with you all today. Today we get to learn about scenario analysis as a tool to aid in forecasting, evaluating, and communicating outcomes of potential actions under varying conditions. We'll also take a look at the mechanics of the scenario analysis process and application to use-based projects. Okay, at this time, I would like to introduce our speakers today. Ms. Derixa Hernandez-Abrams is a research ecologist with the ERDIC Environmental Laboratory Ecological Resources Branch. She works with the STREAM team and the ecological modeling team, integrating ecological modeling to restoration and planning work, improving ecological modeling practices, and assessing environmental impact studies. Derixa is also interested in building a niche with her colleagues in the emergency management world by using modeling and ecology to study the socio-ecological impacts of disasters and improve disaster management practices. We'll also get to hear from Ms. Kara Carrillo today. She is a research civil engineer with the Wetlands and Coastal Ecology Branch in the Environmental Lab at the Army Corps of Engineers Research and Development Center. In this position, she works with ecological modeling of species and ecosystems, and in the last 3 years has worked with the Integrated Ecological Modeling team to support the Bureau of Reclamation, Mobile, Seattle, Portland, and Honolulu districts. Ladies, we are very glad you are virtually here to share your work in scenario analysis with us. At this time, you can share your screen and we can begin.
Great. Second time's the charm. Like I said, my name is Kara Carrillo, and myself, along with Derixa Hernandez-Abrams, will be presenting on scenario analysis in ecological modeling and management planning. This presentation is accompanied by a technical report that was part of a project that was led by Dr. Todd Swanek and Dr. Kyle McKay and funded by the Ecosystem Management and Restoration Research Program. Next slide, please. The objectives of this presentation are to highlight the use of scenario analysis as a tool for addressing uncertainty in potential project outcomes. We will also describe 2 different examples of different types of scenario analysis and present the application of scenario analysis in water resource management project planning and decision making. So to start, what exactly is a scenario analysis? In simple terms, a scenario analysis can be defined as a method for exploring alternative futures and trajectories in systems. It can also be a powerful tool that can be used to evaluate how potential project outcomes compare to each other by incorporating qualitative and quantitative understanding of the system of interest. Scenario analysis can be used to develop different formulations or hypotheses for a system of interest, or to see how a system may be altered under different driving forces that lead to possible changes. In project planning, scenario analysis can be used for decision support and strategic planning to gather collective inquiry, advocate for change, for long-term planning and policy making, and for science and research during assessments, exploration, and speculation for processes, and to consult with experts, stakeholders, or the public. In general, scenario analysis can be used for scientific communication, education, and public information and outreach.
Okay, so this is Derixa Hernandez. I'm going to walk you through the mechanics of the scenario analysis process. So this right here is the general mechanics of the scenario analysis. And we're going to look at the steps, and the first 3 steps, for example, look a lot like steps of the scientific process. And what they're doing is that they're trying to help us focus on the project goals and to accomplish the project mission. So in order to guide the scenario analysis along with the project goal, we're using those 3 first steps. So the first step is the decision problem. We're going to start with a problem, and we're going to next brainstorm what the components of the systems look like. So what is affected by the system in question? What are the stakeholders? What are the organisms that are involved in the system? And third, we're going to formulate a question that is directly pointed at the decision problem. So fourth, we choose the management alternatives that are going to help us solve our problem and answer our question in the system. And fifth, we build the scenarios in order to assess what are going to be the potential outcomes of the system in question regarding the different management alternatives and the options that we have. So the sixth step is identifying what our potential outcomes are, and we do this through qualitative modeling and quantitative modeling, or semi-qualitative modeling. And lastly, we evaluate all the scenario outcomes after the modeling processes. So now I wanted to focus in on the building of the scenario steps. This is step 5. So first, when you're building a scenario, it is a good practice to articulate your system narrative. So we write down how the system works in the present and how it has worked in the past, if possible, if we have historical data. The next step in the building process is to link the system dynamics. So we're going to list the main drivers of change in this system. What are the biological, physical, and chemical components that drive changes in the system? The next step is to link the system dynamics. So we're going to identify the relationships between system components that are crucial to the project goals. For example, relationships between the chemistry of the system and water quality, between precipitation in the system and the desired water levels that we want, if it's a river or a lake. And those are just a few examples of that. So the next step after that is to list all the possible future scenarios that could change in the system. So we're going to pinpoint scenarios that are affecting the system components and the dynamics. For example, this could be land use change or changes in precipitation in your system. Then we're going to match the possible future scenarios to management actions that can help us reach our project goals in the system. So we're going to connect feasible management actions identified in step 4 of the general process to the relevant scenarios listed in step 5C. For example, if your problem is invasive species, for example, a management action could be biological control actions. If your problem in the system is increasing agricultural land, that affecting water quality, you can connect that with a management action like a riparian buffer zone, for example. So the next step is 5F, which is to build a qualitative model. We're going to map out what we've identified about the system into a qualitative model that would serve as a guide for a quantitative model if needed. This could be in the form of a narrative, a table, a diagram, a conceptual model, for example. We got to make sure in this step to list all the model assumptions and to document these assumptions well. So after that, in step 5D, we're going to develop we're going to choose the input parameters that are going into the quantitative model. So we're going to translate that information that we've obtained from the previous steps into measurable parameters for each of the scenarios. For example, number of invasive species, percent of agricultural land, amount of nutrient from fertilizers that are going into the water, and percent of connectivity in the system or amount of precipitation, passage rate are different parameters, examples that can be done. So for the final step, we can build a quantitative model in order to help us assess the system and those relationships in the system. And for this, we use the input parameters that explore different relationships between the system components, the scenarios, and the management actions. And we're going to do that mathematically. So I have some asterisks next to steps 5D, 5F, and 5G, and this is what they mean. A scenario analysis can include just scenarios, for example, or just management actions. So that's why I put an asterisk next to that one. And also, the steps for building a quantitative model are only needed if you do a quantitative model. You can do a scenario analysis with a qualitative model. It depends on what your problem is. So steps 5F and 5G are not needed if you only stop at building a qualitative model. So this slide right here, this is a workflow that summarizes the previous two slides, and this shows the overall process of the scenario analysis, from your decision problem to your assessment and questions, and then how you choose your management actions and your scenarios, and how you evaluate the project outcomes at the end, and compare the possible ecological outcomes, for example, in the end. So before we continue, I wanted to mention a couple of considerations when we're thinking about scenario analyses. So I wanted to highlight something really important, and it's that scenario analysis does not predict futures in systems. It does not give us a certainty of what a future is going to be definitively. It is simply another tool for collecting information and making informed decisions, but we must recognize that it has limitations. So once the scenarios are built and modeled, we can also run risk analyses that may be conducted to explore the negative effects of scenarios and management actions that could happen in the system. Another thing to take into consideration is that scenarios do not have equal probabilities. You can run them through statistical models that can give you different chances of occurrences of each scenario, but the idea is that they're supposed to tell you different stories of possible futures. Also, a good best practice is that you must always have a baseline scenario included in your scenario analysis in order to compare the outcomes to the current state of the system. For example, at UFACE, we do future without project scenarios. In other types of different scenario analyses, they use a lot the term business as usual, what happens if we don't change something. And finally, something that's relevant to now, an example is what happens when you do no social distancing in a pandemic versus applying social distancing. So best practices in scenario analysis. There is guidance on scenario analysis for sea level rise in UFACE, and we took some general best practices from that documentation and adapted them to be used generally in almost all types of scenario analysis. So the first one that we took is that multiple scenarios help address uncertainties for which no reliable or credible probabilities can be obtained. So when there's no credible probabilities available, we can use multiple scenarios to help us get more information. Assumptions must be explicitly documented in order to make your scenario analysis transparent. Alternatives should be considered and evaluated for the entire range of possible scenarios. So your alternatives should be chosen, for example, if you have all the way from a best case scenario to a worst case scenario, and they all should be evaluated. Sensitivity and risk of management actions to different scenarios should also be evaluated, and that is another best practice for scenario analysis. So in this slide, I wanted to show examples of scenario analysis. So like I mentioned, you can have a worst and best case scenario analysis. You could have types of scenario analysis that have to do with things that are affected by climate change, for example, changes in hydrology and precipitation. You can do scenario analyses that involve land use change. So if the land is going to be more urban versus more agricultural, and how that affects systems. There's also scenario analyses on biodiversity change. And the relevant example of a pandemic one is a disease outbreak scenario analysis. In this figure right here, I just wanted to show an example that's common in USAID project planning. We use this in restoration projects where we compare a future without a management action scenario with the future with a management action and what that looks like in terms of the restoration benefits. And we evaluate that throughout the project's lifetime. So next, I am going to start explaining a semi-qualitative example of a scenario analysis using an anadromous fish. So this is a hypothetical problem. So in this problem, the stakeholders had a habitat restoration project for a sensitive anadromous fish. In the assessment, they found that endangered anadromous fish in U.S. Northwestern watershed was being affected. And the question was, how do hydrological changes affect the ecological outcomes of management alternatives in this project, in this watershed? The management alternatives in this case were a no-action plan in order to evaluate and compare actions, an increase in river connectivity at all dams in that watershed in order to increase the migration capacity of the fish, and reforesting 100 meters of riparian buffer zone throughout the river system in order to improve habitat quality for the anadromous fish. So they built scenarios using possible futures, and they did that by studying the historical range gauge data and using that as a proxy for hydrological change. So in this hypothetical system, they didn't have water level data, but they used precipitation data as a proxy for hydrological change. The potential outcomes were plotted into a semi-qualitative bubble chart that I'm going to show you. And in the end, the stakeholders evaluated if the alternatives or the scenarios, in fact, were going to improve water quality, and they assessed trade-offs between the alternatives under different scenarios for the fish. So this is the semi-qualitative bubble chart. The y-axis shows the management alternatives, which are no action, an increase in fish passage, and the increase in riparian buffer zones. So since these systems are always very complex, they evaluated both the overall quality of the habitat and also the connectivity on its own for each of the alternatives. And that's what's in parentheses as habitat, that's the overall quality, and con is the connectivity and how that changes throughout the scenarios. So the x-axis is the lifespan that they were evaluating. So they chose from year 0 to year 25 of the project. And if you can notice, year 0, all the bubbles have the same size. So they all start in the same state. And they evaluated all these alternatives under 3 different scenarios. There was a decrease in precipitation scenario, no change in precipitation, and an increase in precipitation scenario. So the outcomes were represented by the bubble size or the circle size. These are ecological outcomes, and which are a measure of the ecological benefits that are represented by the size range of the bubbles. So it goes from less than 20% to 100%, and a smaller size is equal to less benefits, and a larger size means more benefits over time. Okay, so I'm going to walk you through this first piece first, because I know that this graph is pretty busy. So here they use the no action to compare that to the action plan. The no action is on the top in green. And under a decrease in precipitation scenario, we see that if there's no action taken at this system, the ecological benefits decrease over time. However, if there's a passage increase or buffer increase, those ecological benefits aren't as affected as not taking any action. And then they evaluated the same under the no change in precipitation and the increase in precipitation scenarios. So under a no change in precipitation scenario, we can start to see that if management actions are taken, that increases both the connectivity and the quality of the habitat over time. And under an increase in precipitation scenario, we can also see the same. Okay, Carol?
Thanks, Drixa. So for a quantitative example of a scenario analysis, I will be talking about a freshwater mussel model. This model arose from a workshop between members of ERDIC and the USACE St. Louis district. The decision problem was that freshwater mussels are the most imperiled taxa in the United States and occur in the majority of all the river systems in the U.S. The assessment was that USACE needed to develop a model that forecasts impacts and benefits of project action on freshwater mussel communities and is flexible enough to cover the North American freshwater mussel species. The question for the project was, how will different USACE ecosystem restoration activities affect not only the mussel species, but also other sensitive species that might be in the region? The management alternatives were assessed by how the Habitat Suitability Index increased or decreased with changes in the individual variable HSI ratings. And just as a refresher, the HSI is a numerical index that represents the capacity of a given habitat to support a selected species. The HSI ranges between 0 and 1, with a score of 0 meaning the habitat is not suitable for the species, and a score of 1 meaning the habitat is completely suitable for the selected species. So, next slide please, Drixa. Maybe, oh there we go, okay. So when the workshop participants were building scenarios, they decided upon different environmental parameters, which will be discussed in the next slide. Potential outcomes were derived from communication among the participants as ranges in HSI that would be considered acceptable for a proposed ecosystem restoration. The outcome of the model was evaluated after the model had been completely filled out and the total habitat suitability index had been evaluated. Next, please. The variables that were decided upon during the workshop can be seen in this conceptual model that's shown. There were 5 compartments that were agreed upon as being most important for these mussel species: connectivity, diversity, structure, water, and functional. Out of these 5 compartments came 7 parameters that are critically important for freshwater mussel species and will be directly influenced by the implementation of proposed restoration plans. And they are barriers to host fish richness, aquatic cover, substrate, adult temperature, juvenile temperature, and flow regime. So each of these parameters was given a baseline or a current score. The Habitat Suitability Index is calculated based on equations that were derived from peer-reviewed literature and subject matter experts. And these sets of numbers can be seen in the columns under the blue headers. The life of this project was to determine what the habitat suitability would be in 50 years. But for the purpose of this presentation, I'm only going to compare the baseline condition in the year 1. And these numbers shown here are just a hypothetical example of how the model works using the Merrimack River system in Missouri as an area of interest. So as you can see, the initial HSI score was 0.43, which indicated a marginal habitat for freshwater mussels. However, after restoration effects were put into place for aquatic cover and for the substrate going from poor to suboptimal, the HSI increased to 0.54, which indicates a suboptimal habitat for freshwater mussels. So a change or an increase in those 2 variables raised the HSI score to a more suitable habitat for these mussels. Next, please. Thank you. There are a few takeaways that we would like to note as we wrap up this presentation. The first is that scenario analyses are used to compare potential project outcomes and to aid the determination of future strategies and actions of different projects. The next takeaway is to reemphasize that scenarios do not predict futures. While scenarios can predict potential outcomes, they cannot guarantee what will happen in the future. The goal of a scenario analysis is to best understand the uncertainty that can alter the decisions we make, at least in terms of feasibility. And it is important to note that all assumptions must be documented and communicated amongst all stakeholders when determining what different scenarios are going to be. The last thing we would like for you to take away from this presentation is that scenarios are not equal in probability. And as Derixa said, you can run them through statistical models that give you different chances of occurrences, but the idea is that they're supposed to tell you different potential stories. Next. And in conclusion, we would like to thank EMRRP for funding the project. We'd like to thank our reviewers, Dr. Kyle McKay from ERDIC Environmental Lab and Nathan Richards from the EcoPCX. And our contact emails are here if you would like to email us once Courtney sends out the slide information. And thank you for listening to our presentation, and I'll now open the floor for questions.
Great. Thank you very much, Kara and Derixa. All right, we received one from NAP. What was the name of the study on the Merrimack River, and who is the point of contact there?
Yes, the point of contact for this project, there were a few of them. One of them was Dr. Todd Swanek, Dr. Brooke Herman, and Dr. Todd Slack also worked on this project. And if you would like, I can send you their information for you to get more on that.
And Kara, this is Todd. Dr. Kat McCain from the St. Louis District was our contact at St. Louis.
Okay, great. Thank you. I know I was forgetting someone.
Okay, we've got another question. Can you point out the related publication for these methods, which was mentioned?
Yes. The related publication. The technical report that was for this presentation, yes. It is in peer review, or not peer review. It is past our internal peer review right now, so not published, but I can definitely get you that information if you would like to read more in depth on what we presented today. I know it says anonymous, so I'd have to get whoever that was to send them the information.
Okay, so right now, since it's not formally published, they need to contact you for access to that paper, but you're happy to share it in draft form. If that's finished in the near term or when it is finished, we can post it along with the recorded presentation as well.
Great. That sounds great.
Okay. Did you look at any criteria such as robustness or regret to look at the effectiveness of alternatives, or robustness or regret?
We specifically concentrated on scenario analysis, and we added the risk analyses and other types such as sensitivity analyses as like extra information, but we focused in on only scenario analysis.
Okay, here's some more. What were the assumptions made for creating a model for freshwater mussels across all of North America? Why not make a model for each region, such as the Northwest, Southwest, et cetera? And then is the thought that these assumptions should be made for other species moving forward and all models should cover North America?
I was not a member of that workshop, but Dr. Todd Swanek was, and if he would like to answer that question, he can give more information as to why it was across all of North America.
So, yeah, thanks for the question. So that's that's something we've actually been discussing quite a bit about. One of the issues that we've run into from a planning perspective is that what we were after when we were developing the model across for the nation was trying to come up with a way that we could have a generalized mussel model for project planning, so that each particular region wouldn't have to certify their own model. And this model is really, it's designed to be pretty modular, so that you can actually apply parameters for specific regions, but it's all contained within one modeling package. And so to answer your second question, not all models are probably going to be able to cover all of North America for all the species. Freshwater mussels represent a unique case. What we are trying to do with some of our other research is develop generalized approaches for species-based or habitat-based modeling for restoration. Right now we're taking it on a case-by-case basis, but we are actively trying to figure out ways to develop more generalized approaches for environmental or ecological habitat or species-based modeling. Over.
Any other questions for Kara or Drixa and team?
Yes, hi. I'm the person who earlier asked about the point of contact for the modeling, and I'm sorry I didn't catch the full name of the person.
The question for the study on the Merrimack River?
Yes.
There were a few points of contact from within the ERDIC team, and they are Dr. Todd Swanek, Dr. Brooke Herman, and Dr. Todd Slack. And Dr. Todd Swanek is on the phone right now, and he mentioned the point of contact at the St. Louis district.
Was Dr. Kat McCain, Catherine McCain?
Okay, thank you.
Sure.
And the model is ready to be used by others? Or is that in review also? I missed that part.
The model's in review with the EcoPCX, and it should be ready to be used pretty soon. So we're going through the final stages of the review with the EcoPCX for certification.
Great, thank you. So Dr. McCain is who I should be in contact with to see when it's available?
No, that would be me, Dr. Todd Swanek.
Okay, will do. Thank you very much.
Sure.
Great. Well, thank you. Back to Kara, Derixa, do y'all have anything else for us before we wrap up?
Thank
you for, yeah. Sorry. Thank you for joining us. If you guys have any questions on the document itself, you can contact me or Kara, and our contact information is there. You can take a picture with your phone or something. Or also Todd Swanek is also a co-author in the paper. So we're excited to wrap it up and make it available for your use. Thank you.
Thanks very much. And thanks, audience, for tuning in. I do want to mention that we've got another restoration webinar that will be hosted next Wednesday titled How Much Model Complexity is Needed to Make Environmental Flow Recommendations. And that's going to be presented by Dr. Kyle McKay, one of our frequent contributors. So please watch for an Outlook invitation for that meeting next Wednesday. And then I've also posted a link in the chat box. And if you would please click that and provide us a little feedback on our meeting today, we'd greatly appreciate it. It should take 2 minutes. It's about 6 questions.
Can you please post the link to where we find the recording of this?
I will, and it'll. I'll email everyone that link following the meeting if that's okay. It's not posted yet, but yeah, when I get done here, I'll go copy that link and share it so that you can.
Thank you so much.
That. I will.
Thank you.
Okay. Well, thank you all, and thanks for your patience as we worked out our bugs at the beginning. And with that, we'll conclude our meeting. Hope to see you all virtually next week.